Hello class and welcome to the Chapter 3 lecture. This one is going to be significantly, I say significantly, it's going to be shorter than the other two, let me put it that way. Like I said, we're kind of honing in on, more specialized material here. Some of it is lengthy, some of it is not. We have kind of less ground to cover this time since we're a little bit more focused. So we'll just go ahead and jump right in. Now, Boolean logic. This came about. There was a famous English mathematician by the name of Sir. He was royalty, Sir George Boole, who kind of showed that any problem can be broken down into constituent parts until it represents, true or false propositions. Now. That's where the name Boolean comes from. It's a capital B. Has to be a capital B. Boolean values are either true or false, correspondingly. In fact, they're so common, so useful. Some of these math findings seem to be obscure and weird, but, any new knowledge can be really groundbreaking applied in the right fashion. So, and actually, Sir George Boole, his findings came about way before computers. I think it was late 1800s. So, he didn't have any idea at the time of the significance. However, look, there's even a built-in data type bool. You see that? You see how it turns purple? And remember how we talked about, purple means reserved word or keyword? Well, that's a data type, bool. And Booleans, by convention, they'll start with is. So, I don't know, what will we say? We'll say bool is even, right? Because remember we talked about that modulo operator. I want to kind of beat that into your heads here because it's a really useful one. Here. Here, I'll tell you what. Let's say give me a val and I'll tell you if it's odd or whether it's odd. All right. Booleans can be true or false, right? I'll just assign it an initial value of false. And see, reserved, right? And I could also say true. Boolean expression will require some evaluation. So what we'll do is we'll start with an easy one, an if statement. So we'll say if, how do we test whether it's odd? If input, remember %1, if input %2 is 1, then it's odd. Now this will be an easy segue into this as well. Now that we covered if, else. All right, so what do we do here? Oops, darn. What did we do here? All right, so what we did is we declared an integer that we're reading in from the console. We have a Boolean. We want to know if something is even. Oh, no. We want to know if something is odd. Whatever. I'll give you a number. I'll tell you if it's odd, is what I, kind of display to the user. Then they give me a number. If it is odd, then I store true into this Boolean value. Otherwise, I store false into it. Notice I don't really have to do that because I already assigned an initial value of false. I don't have to assign an initial value. I just usually do. Then I display the results. So let's see. Oh, that's right. Is odd. Sorry. Duh. Odd. What? Oh. 9. Yep. And I'll say 8. Now note, you see this. Note 1 and 0. All right. So this is a good point. This is what I wanted to illustrate here. 1, true, is 1. False is 0. So really, the Boolean logic dictates that a 0 is false. Anything else is true. So 1, 2, 3, 4, 5 is going to be true. Looks a little bit silly coming out on the console, but that's the case. Okay? True. Now, so then what I could do, Boolean values are, that constant true, false. Those are just basically synonyms for 1 and 0. Yep, 9 is odd, 6 is not. Oops, darn. So there you go. So Boolean's true or false. Basically, a true is a 1, or any number other than 0, and 0 is false. And so this is our if. This is a typical branch here, if else. If, note in the parentheses I have my expression. Now, note that this expression also evaluates two Boolean condition. Input %2, input modulo 2. If the result equals 1, then yes, we're odd. Now, notice I have equals instead of equals. Equals is for assignment, right? That is for assignment. Equals is for comparison. That's the comparison operator. So if input modulo 2 is 1, that means it's odd. Is odd equals 1. So after the if, I put my block here, and anything in the block, this is basically what I want to execute if the number's odd. Otherwise, notice the else doesn't have, nor does it need the condition here, because it'll basically catch anything that the if doesn't, so you don't need any sort of evaluation there. In other words, in every other case, other than the input being odd, other than the input being odd, we set is odd to false. And so I said, remember, equals versus equals is assignment, equals is a comparison. This means not equal. This is also comparison, but it means not equal. So what I could do, I could flip this around, and now I've said if the input is not odd, then is odd equals 0. Otherwise, is odd equals 1, because we know it's odd. So the result of this should be a Boolean expression that evaluates a true or false. Your if catches this case only. Otherwise, you have kind of your default. Every other case, which is where we assign 1 to is odd in this case. So I hope that kind of made sense here. If not, let me know. Just kind of look at the example, do a couple yourself, and step through it. And let's do this. Let's decide whether a couple numbers are really high. I don't know, let's say. If x is greater than, I don't know, what's a big number? 1,000. Watch this. And, that is a Boolean and expressed in C++. If x is greater than 1,000 and y is greater than, I don't know, 1,000, large numbers. Otherwise, oops. All right, so we'll say 9999, 9999. I should get yes. Yeah, large numbers. Now, if I have 9999 and 0. Oh, wait a sec. Hold on. If x is greater than 1000 and y is greater than 1000. Oh, silly mistake. There we go. 9999 and 0. Nope, not large numbers. Because while x is greater than 9999, y wasn't. And we can even flip these around. We'll say 0 and 9999, and it'll still know because both of them are not true. Now we can extend this. You see I have else if up here. Basically what I'm doing is saying, hey, are both numbers large? Otherwise, they're not. What I could do is I could add another branch and say else if, same, Boolean condition goes here, and then my code goes in the blocks. Else if x is greater than 1000 and y is less than 1000. One is large. So now let's give 9999 and 0. Yeah, one of them is large. And the same, it'll execute both statements. Yeah, not large numbers. Why did this last one happen? Because x was small and y wasn't. Now, this is where we can use Boolean OR. If x is greater than 1000 and y is less than 1000, or y is greater than 1000 and x is less than 1000, there we go, 1 is large. Now, I've caught both cases. So in other words, if both are large, fine. If one is large, fine. And then if none are large. And this would be much clearer if we did this, right? If we showed how we wanted to compare it, how we wanted to force the comparison. This way, we see explicitly, hey, if x is greater than 1000 and y is less than 1000, or y is greater than 1000 and x is less than 1000, it's more explicit when I put the parentheses around the expressions this way. If I have this specific case, else if I have this specific case. You might say that's two cases, but it still evaluates to one case because we have a Boolean and or another Boolean and. So this is the Boolean or. So then this one, for example, this last one, this would be false or true, if either of these is true. Or if I flipped it around and had 9999 and 0, this would be true, and then this one would be false, but this branch would still be true because one of them is true, because we have the Boolean or here. We have the, this is a pretty good one. We have the not operator, the Boolean not operator here. So watch this. I can do this a couple ways. I say if x is greater than 1000 and I can also say if x is not less than 1001. That's the Boolean not operator, negation. So they should both evaluate to the same. Let me get this cleaner so I can see what I did. Let me pull this into the appropriate indentation level. All right, int cnx if, I didn't close this bracket. if x is... Oh, duh. So we'll enter x, 999, not large. Now, if I enter anything greater than 1,000 or 1,000 or, yeah, greater than 1,000, yeah, both evaluate to large. So you see what I did here? If x is greater than 1,000, go ahead and display large. Otherwise, if x is, if not, then the Boolean expression, if not, x is less than 1,001, which means x will be 1,001 or greater, then we'll display large. You know, I could also do this equal. There we go. Now we're looking at 1,000 as the threshold instead of 1,001. Kind of logically makes more sense. So that's the Boolean not operator, the negation operator. And we can flip this around. If we say not, two knots make two negatives make a positive, right? So watch, these will differ now. Yep, large and then not large. Right? We only have one large. And then we'll switch it up, and now we have a large. Because what this is saying down here is if x is less than 1,000, then we'll display large. So we could actually kind of, to make this, have this make more sense, if it is not the case that x is not less than 1,000, in other words, if x is less than 1,000, then we'll see out small. We'll display small. There we go. So you kind of look at these and kind of create nested Boolean expressions that kind of make your head spin. You know, you can really get complex with your logic in there if you want. So Booleans are small, but you can kind of build on them, and they're very, 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 very useful. So I could also and I could have a nested if here. Oops. Didn't mean to do that. Didn't mean to build. So there we go. So basically, if both x and y are greater than 1,000, if x is 1,000, only if it's greater than 1,000, then will it check to see if y is greater than 1,000. Then, if both that's the case, it'll say both are large. Watch. 1,001. Ah, darn. There we go. What is it? Oh, duh. I need two numbers. There we go. Both numbers are large. So here, how about this? This will make it clearer. Let's not even here. Let's do this. Yeah. This is a good one. All right. So if I say if x is 1,001, what do you think will happen? We won't even enter into this branch, so we should never execute this portion of code, right? So if it's 1,001, even if y is greater than 1,000, it'll never hit that branch of code because we don't pass through this initial gate here, the x greater than 1,002. All right. Yeah, and so what we can do, if we have one statement we want to execute, we don't need to wrap all of this stuff. If x is greater than 1,000, then we can just display large. X is large. And it'll compile, it'll run fine. You could even nest these. There you go. Now, if you have more than one, and be careful, because what happens in this case if we say, like, 1 and 1? Uh-oh. Well, remember I said if you have more than one statement following your if, then you'll need to wrap it in brackets. We have one following x and y are large, and then that's it. It will continue. It will consider it to be out of these ifs, and then it will just print this unconditionally. So, if you have any doubts, if you think this might be an issue for you, always wrap your code in brackets, even if it's only one line, because who knows, you may add another line later, and if you can't keep track of that, then don't worry about it, just wrap, and you're fine. Now, if I put 1 and 1, nothing, right? Because I've wrapped this all into the same block. So all executes as a single block. Only if y is greater than 1,000, which is only hit if x is greater than 1,000. Right. We've got nested ifs, optionality braces for immediate statement. Yeah. So again, your order of operations. Like I said, your parentheses are first, your unaries are second. Unary is the Boolean not, and the negation operator, the minus, which turns stuff into a negative number. Then you have your arithmetic, remember exponents. Well, you have multiplication, division, addition, and subtraction. Your relational operators, your comparisons, inequalities, equalities or inequalities, greater than or equal to. Less than, greater than, less than or equal to, greater than or equal to. And those are written in C, by the way, those are written, the less than or equal to, I think we saw this already, less than or equal to, or greater than or equal to. Boolean and then Boolean or. Those are kind of the lowest precedence. So you'll need to refer back to these, occasionally, I guess, if something kind of throws you for a loop when you're evaluating expressions. And you'll go back to the book and look at the kind of the order of precedence of the operators. Be aware you also have a Boolean and, or a bitwise and a bitwise or. You'll see these. You can see these for encryption and similar, bit level operations. You can have bit shift operators. So, don't worry about this too much right now. Just don't be surprised if you ever see a single and or single or. Switch. Switch is an if on steroids. So let's say I could have like 10 choices. I don't know. All right, let's do... enter A for apple, B for banana, C for I don't know what's a food, cantaloupe, D for I don't know dog, E for echo, F for fruit, G for golf. All right, I could say if choice is A, right, if it's equal to A, then, whatever, I'll say, apple, if, blah, blah, blah. So that's just a whole bunch of, else ifs. So that's kind of a whole bunch of, kind of constructs there. Some things, when you have a whole bunch of choices, may be more apt, kind of more, may tend toward having switch as a logical solution. So switch statement basically says switch on whatever the expression is, in this case choice. We're looking at choice and we'll switch depending on the values. You'll see why it's called switch. Case A. Then we're done. Otherwise, if it's B, then we'll say banana. Otherwise, and so on down the line. Now watch what happens when I get to the end here. Oop, darn. Now, we have a default. We have a default condition in switch. Oops. So it catches every other case. And I don't even really need the break there. So you see what happens? We switch. Basically, I say, hey, where you got a whole bunch of cases coming for, or, I don't know, one or more case for this input value, which in this case is choice. So we have discrete, a set of discrete values in a character up to 255, right? So I say, hey, if it's A, then we'll say apple. This break is important. This break is really, really important. You need to put it there or else you'll fall through to the next case. Because watch this. All right, A, apple, all right. I'll make it a little cleaner looking. Now, if I remove this one here, I'll fall through to the next case. Uh-oh, won't. So you need to put that break there to divide. That's a very common error. You need to put that break there to divide the cases. Break will basically break out of this construct, this switch construct. So we'll say you're done. You're done. At the end, anything that doesn't match A, B, C, D, E, F, or G will execute the code after the default label here. That is just a reserved keyword, default. And this is the this is the syntax for a switch statement. So a switch statement could be a little more orderly maybe than a whole bunch of if, else if, else if, else if, else if, else if. It just seems a little more natural for a lot of choices. For something where you have a lot of choices. Okay. Oop. All right. Yeah. So here, we can compare, we have the relational operators, right? If, 1 is less than 3, then, hey, true, say true. Because that's a Boolean expression. That's definitely true. Yep. I don't know where that break came from. What happens if I do this? Let's see, let's get crazy. If A is less than A, see out true. Uh-oh. How did that happen? Well, remember we talked about characters as integers. A, lowercase a, is 97. Uppercase A is 65. Let me switch this around, sorry. Oh, darn. There we go. And then if I switch the operator around, A is greater than A. Why would that be? Why would that be? Well, lowercase a and uppercase a are different ASCII values. That's why. Lowercase a is 97. Uppercase is 65. This is why you cannot compare character values directly. There we go. It's why you cannot compare character values directly. And, a lot of string comparisons, if you do string comparisons, it does it ASCII-betically. Oops. Darn. There we go. So false. Let's see. Oh. That's not right. There we go. 1. So hey you. So what it does basically for a comparison program, and programs use comparison for sorting. When you're sorting, let's say you want to sort names. Well, you use comparisons for sorting. In this case, we know the lowercase h for some reason the lowercase values have a higher ASCII value than the uppercase values. So in this case, it considers hey you to be greater than the uppercase hey you, and this. Yeah, because we evaluate to true here, and this has implications because for sorting, when we sort names, if you just use your standard sorting library for strings, be it Java or C++, whatever, your standard comparison, you have to override the comparison. Otherwise, you'll get issues. We can see, what the heck here. So you see, we can get some weird stuff. Uppercase before a lowercase before upper. Zeros and ones depend on where they fall. If you go back to the ASCII table, and this is where this all comes from, right? And so you get some strange behavior, especially when some names are shorter than others. Oh, well, here. Let's see. Yes, so Patrick would come before Pat Brooks, and that doesn't really make much sense, does it? So anyways, this is a funny quote that I like. So you'll have to override these, and we'll get into that later. Just be aware that you can't compare, or at least you did tread on very thin ice if you're trying to compare certain values like characters and character strings. So this kind of segues into this funny quote. Silly me, I just figured that alphabetical sorting was, and this is out there on the internet. It's an actual really, famous in small circles quote. Silly me, I just figured that alphabetical sorting was such a common need, judging by the number of people that asked me how to do it. I'm not wrong either. That I wouldn't have to write the damn thing. Meaning your own comparison. But I didn't count on the stupid factor. Jesus Christ, people, you're programmers. You're almost college graduates, and none of you know what the alphabetical means. You should all be ashamed. If any of you are using your language's default sort algorithm, which, like I said, uses comparison underlying, we get silly stuff when we compare characters and strings, which is almost guaranteed to be ASCII-betical, right? Going by, and by that we mean going by this table. To get alphabetical sorting, you should proceed to the nearest mirror and slap yourself repeatedly before returning your desk and fixing your unit test that didn't catch this problem. Meaning, you know, if you put some funky stuff into production, and you should have known better. We saw function return values. We dealt with this last time. You know, remember we had the double quadratic equation. Took 3 doubles. Oh no. So a return type is the double. That's the value that we have to return. It has to be of type double, or at least a compatible value like float or int. So return, what is it, negative b plus or minus, we'll just do plus, the root of b squared minus 4ac. I should put some white space in here to be clear what I'm doing. All over 2a. 1, 2, 3, 2, 1, 0. Yeah, and so I'm balanced on my delimiters here. Yep. So there we go. So that's the double precision value that we're returning. We're manipulating a bunch of doubles, so the result should be a double. And it shouldn't complain at me. No. And what did we say? Oops. 6, negative 17, and 12 for the coefficients. And it was what, 1.5, I think. There we go. All right. String and array indexing. Yeah, so if you have a string, so the string class, like I said, we will pull the string library in for this. So the string class is much easier to use than a old style C string, the character string array. So string class is usable like that, and you can like such, and you can read values into it. You can manipulate it. You can peek. Check this out. See that? What we have here is indexing. So the string S can be thought of as a bunch of component characters, right? You have a bunch of component parts. You have 1, 2, 3, including the space, 4, 5, 6, 7, 8. It looks like 9 constituent or component characters in this string. The first one, in slot 0, strings are 0 indexed. The first one in slot 0, this very first slot, is H. If I change it to 1, what do you think will happen? We'll go to the next slot, space number 2, and we'll display I. There you go. Now, you can also, strings have member functions, which means we can use the name of the string, the dot operator, and then use this member function at to display what's at slot 0. And basically what that does is the same thing as the index-based approach. There you go. Or I can also call dot at on 1. So here we basically instantiated a string. We say, hey, we want a new object of the string class called S. Now for S, I want to know what is at slot 1. Now what happens here? There's no slot 99. What happens? My compiler doesn't complain. It must not be a problem, right? Ew, out of range. So the same thing happens too if we index out of range. You can't overrun the bounds or else you get problems. Your program terminates. Dot at. Oh yeah, we can change it. We could say. Oops, darn. So we should overwrite the sixth 1, 2, 3, 4, 5 THXRE, I guess is, yeah, there we go, is what we'll get. We could also say instead of X, we could, here, the one next to it, we can make it Y. And then we'll have a Y there. So we'll have what? THXYE. That way we can overwrite that value, that character in the string. Yep. Yeah, strings have other member functions. You can see the size of a string, which we said what would be 9. And it also has an append member function. So we can append onto a string. All right, so size would be 9, then we'll append. Oh, and then we'll look at the size again. That'll be a fun one. All right, hi there, whatever, or jumbled, hi there. Size is 9. And then after I append all this stuff, so I guess 6, 1, 2, 3, 4, yeah, 6 occurrences of HE, which would be 12. 9 plus 12 is 21. That's the new size. And again, you got to be conscious of how this stuff looks. There we go. So we'll kind of format it a little neater. If you do a lot of Java, you'll forget about this because you'll be using more than likely, system.out.println line, which will print implicitly a new line character at the end of the string that you're outputting. So you'll tend to forget this stuff. And then you come back to it and you're like, oh yeah, I need to start getting cleaner again. Okay. Yeah, out of bounds. We looked at out of bounds. If you overrun the bounds of the string, then it'll crash. The program will crash. Yeah, and so we do have some. These can be useful. You can figure out if something is alphanumeric. If it's A to Z, upper or lower. If it's a digit, 0 to 9. If it's a space, if it's white space like a tab or a space character or a new line. And you can also cast characters to upper and to lower. So, what we'll take, we'll go back to our string. We made a mess here. So, what we'll say, remember those Boolean, Booleans start with is. So we know that that's going to return a Boolean, right? Indicating whether or not it's alphanumeric. I is definitely alphanumeric. I is definite, or it's alphabetical. Excuse me. It's an alpha character. It is not a digit. It is not a space. Oh. We can cast it to upper. So I have a capital I. And what we'll force the H to lower. Let's do that. That'll be fun. So make sure we got what we expect. Too much Java on the brain. All right. Okay. So we have two. Okay, so we have, let's see, cout is alpha. It is alphabetical. It's a non-zero. I'm not sure what the 2 is about, but it's a non-zero, so we know that that's a true. It is not a digit and is not a space, so we have 0 and 0. Now, interesting here, we have the note that 2 upper kind of gives you the ASCII value of 73. So we can cast that. We saw how to cast it explicitly, or we could go to the ASCII table and say 73 is uppercase I. So we say we expect because the slot 1, which is really the second space, is I. So upper would be I. And then we would expect 104 to correspond to a lowercase h. And let's see if that's true. Yes, it is. So we could static type, we could cast this thing, but we can see that we got the results that we expect. Yeah, these are very useful, very, very useful. String manipulation cannot be overstated. So we could look for occurrences of a substring within a string. Watch this. S.find. These are all member functions of string, of the string class. So let's find th within string. 3. So this is the starting space. This is the starting slot for this string, substring th that I want to search for within hi there. 0, 1, 2, 3. That's right. So we did find th, the first occurrence of the substring th within the string hi there at slot 3. So that's how find works. Substring, sub str. I believe it takes 2 arguments. Let me see substring. No. Well, here, let me. There we go. All right. So I is what I get. Now, what is that? I'm starting at slot. I actually got I space. This is I and space right here. I'm starting at slot 1 right here. I want 2 characters starting at slot 1. That's the substring I want of this greater string. So here I got I space. So we'll make it a little clearer. We'll say 2 and 3. So this way, no. We'll say 3 and 4. So this way we'll start at slot 0, 1, 2, 3, and we'll go 1, 2, 3, 4 characters over. So I should get THER is what I would expect the output to be. There you go. Push underscore back, that should be pretty clear. There we go. So now we should get the entire string. Hi there, you sweet. Let's see. Oh, you know what? That's right. Yeah, push back only pushes a character. There we go. So you see my string is hi there. Now we should have hi there with an exclamation point. Sorry, yeah, that was my mistake. Oh, I haven't displayed S again. I was mistaking it with append. Sorry. Yeah, there you go. Hi there, exclamation point. Let's see. Push back. We have insert, replace. We can insert into a string. Another string at a certain place in the string. So let's see what that does. Uh-oh, hold on. maybe it's, sorry, just a sec. Be right back. Okay, sorry, I'm back. All right, so I think I got the order backwards here. Insert at slot 3, blah, blah, blah. Let's see if that's right. There we go. So you see what it did, 0, 1, 2, and then it says starting at slot 3, I'll insert blah, blah, blah. So hi, blah, blah, blah there. Replace. Replace. I think it takes 3 arguments. Yeah, candidate expects 3 arguments to provided. So we're replacing. There we go. So we're replacing 4 characters. We're kind of yanking these 4 out and putting blah in there. So if we change this to 5, we yanked 5 characters out, starting at slot 3, and replace it with blah. So yeah, there's a lot of stuff here. Don't worry too terribly much about it. You know, you'll be able to come back and reference the documentation. Check this out. What's cool is we can, it kind of might blow your mind, but we can actually add strings, and it just does concatenation, which is, gluing stuff together. So here's an example. There we go. There we go. Look at that. Or, we could create a new string variable. I didn't have to, send it into the output stream. There we go. There you go. Look at that. Look at that. Ternary operator. Yeah, and so another construct that you might see, don't be, too horrified by it. You know what, here. Yeah. All right. So what we can do, we can say, hey, for a ternary operator, what we do is we take the result of a Boolean expression. If it's true, then we assign a value. Oh, sorry, just a minute. Okay, sorry, I'm back. So we have, we had our ternary operator. So we have a Boolean expression here, and if it's true, then we'll have whatever some value. Otherwise, we have another value. So the first one after the question mark is the value that results if the Boolean expression is true. Otherwise, if it's not true. So this can be useful in assignment or return. Usually you see it in return values, but you can. I don't know if I want to overload you. We can just we can use this simple example for now. So we'll take our Boolean is 5 and we'll say, hey, if x is equal to 5, then is 5 is going to have the value true. Otherwise, it'll have the value false. So let's see if this. Let's see if this works like we think. Yep. And nope. So yeah, I mean, of course, we knew it was going to work like this, but we can also, like I said, we can use this in return. You'll see this in return statements. So if you saw this in a function, oops, darn, is 5 here. There we go. And this works because it evaluates the result of is5 with x sent into it, and then it will print the result, whether it's true or false, 0 or 1. So let's go ahead. Is5 cannot be... what's wrong? Let's see. Is5 cannot be used as a function. Oh, yeah. Duh. There we go. CC didn't like. I had Boolean declared as 5 here, so it says, "Hey, wait a minute. That's a variable, dummy, not a function." Well, now it's only a function, so I removed all ambiguity. So there we go. Yeah. So now we'll prompt for a value. We'll get it, and we'll say, "Hey, if x is 5, then yeah. Otherwise, no." 5, so we should get 1. And anything other than 5, we should, I don't know, we should get a 0. Yep. Cool. Okay, ternary operators, floats. Yeah, so something important. And I've actually come across this at work a few times. They didn't get it. And these are people with computer science degrees, so yeah, just be aware. This one, hopefully it'll stick in your mind here because you can actually do a lot of good with this one. Let's try this. I'll try to force this one. Point 1, 5. Hopefully this will work for me. It may or may not. Just depends on how the rounding occurs. No match for operator. There we go. Aha! All right, so look at this. We have a double equal to 0.5, and then we have a double that's 1 minus 0.3, which is 0.7, minus 0.15, which is 0.55, minus 0.05, which is 0.5. Well, how are they not equal? Oh, darn. We're here. They look equal on the surface. However, let's see. I'll see if I can force this. What is it? Set precision. What is it? Fixed. Set precision. I don't know. We'll see if this is enough. Oh, yeah, that's right. We have to include the I/O manipulation, input output manipulation library. It's really not. Try it one more time, and then we'll just kind of give up, and then I'll Hey, look at that. All right. So what happens is we have, so in the mantissa portion of the floating point, we have a whole bunch of bits over there on the right side. It is impossible with a finite number of bits to represent decimal values with binary. It's always an approximation. And so what happens when we start to manipulate these things, we lose our exact precision because some zeros and ones are truncated. And so that's why you can't expect doubles to line up even though they theoretically have the same value. So what you can do, you can look for a tolerance within a delta between them. So what we call an epsilon. Now what I could do then, I could have some really small value that I'm okay with, and I could say, oh no, yeah, double one, yeah. I could say, let's see if the absolute value of the difference between these two is less than some really, really small value. That way I can be pretty sure that, that way I can be pretty sure that they're the same number. In theory, you know what? There we go. That way I can be sure in theory that they're the same number anyways. Yeah. Yeah, it's less, the difference between them is less than, what is this, 1,000, 100,000, 10,000, 100,000, 5 millionths. So that's kind of the way you deal with that, is get an epsilon, what we call an epsilon comparison. So your decimals, your floating point values, if you start manipulating them, they likely will not be exact. Because there will be some truncation going on behind the scenes due to the fact that it's impossible to represent decimal values with finite binary values. And then the last thing to mention here on the list, and it's not even really that important, but if I have, let's say, int x equals 5, y equals 2, I won't even bother with the input. So I'll just say if x equals 3 and y equals 4, then do some stuff. Oops. And in reality, this y comparison will never happen. This is what we call shortcut. So if we need both conditions, the compiler is smart. If we need both conditions, it looks at the first one and says, x is not 3, so I don't even care what y equals, since the condition, the branch will never go true anymore. So that's what we call a short circuit. It doesn't even bother to kind of compare the value of y. And the same with or. In this case, it'll say, hey, x equals 5, but since this is a Boolean or here, I only need one of these to be true, so I don't even need to bother comparing, making sure y equals 4. So that's it. That's all our stuff we got this time around. So this kind of concludes it for Chapter 3. Again, you have any questions or difficulties, let me know. Otherwise, I'll see you at the next lecture. Thanks.